Checkout for the hotel is at noon, and if you've checked out and you have bags or you're going to do that, and if you want to attend the sessions, obviously, through 2 o'clock, you can leave your bags with the concierge up on the 2nd floor, which is the checkout desk on the floor above us. Here's an idea of the schedule today. We're going to start out with the keynotes. There are sessions, normal sessions, that will run from 10 to noon, and then we will have the Demo Friday and the HKG18 wrap-up that will start in noon, which is in Ballroom 3, which is next door over here. There's lots of stuff that we're putting up online. A lot of it's up there already at this URL. Many videos are there. All the presentations that we have so far are there. And we'll be continuing to add stuff over the upcoming week. So by a week from today, everything will be there. All the videos, all the presentations, whatnot, but there's already a lot of stuff there. And then, of course, we have our fantastic photographic team from Form AV who have been covering us all week long. And we post pictures up on Flickr, so you can get the pictures up on Flickr as well. And then this afternoon, we'll talk about the Dave Piggott Challenge, the puzzle challenge. And we've had several submissions. And the first correct one that came in will get the big prize. And then any additional ones will be put into sort of a drawing, and that person who's drawn will receive the runner-up prize, if you will. So we had a bunch of rewards last night. And so there were 5-year awards. And so if you're in this room and you made it to this morning and you're a 5-year award recipient, could you please just stand up for a second? Anybody? Is anybody here? All right, so thank you. Congratulations. Yeah. Well done. Thank you so much. And then we also had some interesting slide dynamics and recognition awards. So if you're a recipient of one of the recognition awards, could you just stand up for a minute? Anybody? All right. Great job. Way to go. Thank you so much. So basically, at noon in the ballroom, we'll do some wrap-up. We'll have some lunch in there. It's not a sit-down lunch. It's sort of, I think most everybody's been to Connect before, but all sorts of nice appetizers will be served. There'll be some drinks and whatnot, and you can go around and check the demos out. There are over 25 demos. There's also a contest, thanks to Tomas and the team at Xilinx, who have those really cool Ultra 96 boards, and there are 30 of those. And if you haven't submitted your idea already, there's a URL. You should have access to the URL. Please submit your ideas, and there'll be a bunch of those boards that will be given out. Those look really cool. And let's kick right off, and please join me in welcoming Dileep Bhandarkar, who's come here from Qualcomm, who's going to talk with us about the future of data center.
It's great to see such a big crowd. I was worried there'd be fewer people in the room than there were on my flight last night from San Francisco, but that doesn't seem to be the case. Okay, I'm going to, over the next half hour or so, share what I've observed in the industry, how did we get started, a little bit of history, and then talk about what I see as important things for the future. So with that, let's go. So, a historical perspective of the first 40 years of Moore's Law, and then what happened when Dennard scaling ended, and I'll explain what Dennard scaling is, and then we'll talk about how we shifted to energy-efficient multi-core designs, and then end up with talking about some heterogeneous computing. So the first Shockley invented the transistor in the early 1950s. And over the first 50 years or so, you could see how things kind of transitioned. So over the first 50 years, by the time we got into the 2000s, we had about 500,000 transistors on a single chip. So quite a lot of progress. But the other sort of important thing that happened along the way was the invention of the integrated circuit. And Bob Noyce at Intel and Jack Kilby at Texas Instruments invented the integrated circuit at about the same time. And I was lucky enough to meet Jack Kilby when I first started working in 1973. So here's what the first 40 years of Moore's Law looks like, starting with the 4000 which had about, I forget what the number is, a few thousand transistors, and it slowly kept increasing until we got to over 1 billion transistors, and I think it was either 2003 or thereabouts. 2005, okay, I've got it on my slide. So along the way, there was something called Dennard scaling. Dennard was somebody who worked at IBM, and what he observed was that when you go from one semiconductor node to the next one, there was a constant scaling factor K, and the value of K was 0.7. And what happened was all of the parameters, the physical and the electrical parameters, scaled by that same factor of K. So it was very easy to move from one node to the other. And the important thing is K squared is 0.7 times 0.7, which is 0.1. So you take the inverse of that, that's 2x. So what that said was with each node, the density increased by a factor of 2, which is exactly what Moore's law said. Now, what happened was around 2003-4, Dennard scaling broke down for a variety of reasons because of device physics. And things no longer scaled by that constant factor. It was mainly because the interconnect didn't scale the same way as the transistors did. So you couldn't sort of move from one node to the other without doing something more drastic, like introducing new materials, new processes, and so forth. But the density continued to increase. And that caused a shift in the way we did design. So instead of pushing single thread performance, at that time, we had to move because we had density, but the transistors weren't getting as fast. We had to move to multi-core designs. So the post-Dennard scaling era is about multi-core. Single-threaded performance, and I'll show you, I've got some data, has started to slow down, and performance was driven mostly by higher core count. So here's the plot that somebody at Stanford University put together, which shows on the top, it shows the transistor count increasing, doubling every 2 years. Single-thread performance, which is the blue part, started to tail off in the 2005-6 timeframe. Frequency started to flatten, but in order to get that higher performance, all we could do was increase the number of cores. You can see that those black diamonds at the bottom showing how the core count went up. And when the core count went up, we had to also increase the power budget. So in order to get higher performance, we had to go to multi-core, which had some software challenges, and we had to figure out how to tolerate higher power. So here's what I did. I went and looked at the last 5 generations of the Intel Xeon processor, starting with Sandy Bridge being the one in 2012, followed by Ivy Bridge, Haswell, Broadwell, and then Skylake. And I picked the 130-watt processors because back in the Sandy Bridge generation, the 2-socket servers, the highest power was 130 watts, as opposed to 205 watts on Skylake today. So to do a comparison at the same power level, I picked 130 watts. And what you see is that the blue bar is the spec in 2006, which is a speed metric where if you're just running one core and nothing else, and so you have access to all of the memory bandwidth, all of the caches, the blue bar shows what that number is, and you can see it's steadily increasing. But when you put that in a multi-core environment, and now you calculate the spec-int rate per core, you can't run all of those cores at that same performance, and you see that those orange bars are starting to flatten more than the blue bars. And this was primarily because you were constrained by power. So this is the power constraint chart. Then I said, let's see what that progression looks like if I use the highest power in each of those generations. So if you see on the first one, which is the 2690, which is Sandy Bridge, the TDP was again 135 watts, and then to the right on the red bar, which is Skylake, the top end is 205 watts. Now, if you calculate the other metrics, like the performance per watt and the performance per watt per core, you can see that even when we increase the power envelope, not we, even when Intel raised the power, now I spent 12 years at Intel, so you can't blame me for any of this. I left about in 2007. So anyway, what you can see is that even when you allow the power to grow, that the energy efficiency isn't just quite there. So in the last few years, at least some companies, mostly in the ARM camp, have kind of woken up to the fact that energy efficiency is important. And we certainly at Qualcomm embraced that thought. I pulled this slide out of Peter's Hot Chips presentation last year, and there are a lot of interesting messages here. First, he talks about that ARM is taking their cores beyond just mobile. So they're doing cores that fit more nicely in a server platform. Efficiency is important. And then he has a little subtitle there that the future requires a new approach to CPU design. And part of my talk today addresses that statement. So if you look at the industry, things are moving pretty rapidly from on-premise to the cloud. And most of this, I think, is the public cloud. But a lot of the enterprises are also moving towards a private cloud where inside of a large corporation, instead of each department having their own set of sort of servers, like finance has their own, engineering has their own, a lot of companies are pooling those resources into an internal service that they then parcel out compute and storage capacity to the internal business units. So you can see by 2020, more than 50% of the server shipments will be to the cloud providers. Now, what you see is I started in this business working at Digital Equipment Corporation in 1977 on mini computers. And what I saw over the last 40 years or so is that disruptions always come from below. Somebody finds something that is less expensive, smaller, and that comes in and eats into the lunch of the bigger things. So the RISC systems, mainly from Sun Microsystems, came in and ate into the business that we at DEC had on mini computers. And then the PC technology, primarily driven by Intel, and this was desktop PC technology, came in and displaced a lot of those RISC Unix systems. And then even in the PC era, it moved from using desktop processors to notebook processors. In 2006, Intel launched their Core 2 Duo, which was primarily designed for notebooks. And then the multi-core instantiation of those mobile cores worked in servers. So the next technology phase is happening now with cores that were primarily designed for smartphones, driven by the ARM community. So how do we think about this at Qualcomm, and why do we believe that we can build something that's an interesting set of products? If you look historically, one of the things that Intel has been able to do is because of the high volume economics is what makes everything work. So when the PC volumes really took off, Intel was able to use the revenues from the PC segment to fund the development of new fabs for new process nodes. And that drove the industry, that drove the leadership nodes. So they got to 45 nanometer a year and a half or 2 years before anybody else. And that continued for a long time. What has happened within the last 3 or 4 years is that volume mix has shifted from PCs to the smartphone. I mean, you can go do a search and see how the iPhone took off or how the Android phone took off. And that volume has caused a shift where the new process node is not driven by the PC usage, but driven more by the smartphone usage. So we're able to take advantage of that move and get to a newer node earlier than Intel has been able to. And what does the new leading node give you? One is these transistors are smaller, so you can pack more nodes. The power is lower. And you do get some small amount of speed increase in those transistors. So when you combine all of those features, you can get better performance, lower power, and the area is smaller because it's in a smaller node. And the area is important because that determines what your cost is. So now you can compete with somebody who's on an older node trying to build a larger chip. So we've been taking advantage of this shift. I belong to the server business unit inside of Qualcomm. So we're able to leverage what the mobile side of Qualcomm has been doing to bring in these new nodes into Qualcomm and be able to use it to drive leadership products for the server domain. Our server chips are designed primarily with the cloud in mind. We don't have a desktop legacy that we have to protect, so all of the trade-offs we make is based on server workloads, whereas if you look at the x86, a lot of the decisions they make is that their cores are designed to run well for gaming, and then once they have a core that works well for gaming, they use that in servers. So they're kind of designing for the top and bringing it down. We're designing it for sort of for energy efficiency and scaling that up. And that's a dichotomy that you see in the way in which we are approaching this problem compared to the x86 vendors. Unfortunately, some of the people in the ARM community haven't kind of caught up with that, and they're still designing UC 180-watt parts, which I don't think makes any sense. So yes, the future does require a new operational CPU design. We measure ourselves on performance per thread, not just the performance of a single thread, performance per watt, and performance per millimeter squared. I spent 6 years of, almost 6 years, 5.5 years of my life between leaving Intel and joining Qualcomm, working at Microsoft as part of their cloud infrastructure services team. And when I got there, I had never walked into a data center before, didn't know what was important to the data center customers, and it was an amazing learning experience. It's amazing how you think about things differently when you are providing silicon that you think is, better than sliced bread, and the customer is sitting there and saying, why the hell should I use this? So I learned that when you're collecting money from a customer versus when you're paying for what the supplier is offering, it's a different point of view. And I learned a lot from that experience, and I'm using that in my work with the rest of my colleagues at Qualcomm. So when they look at how they deploy servers, it's all about energy efficiency. And if you look at the total cost of ownership of servers in a data center, it's not just what you paid for the servers. There's other equipment, there's networking equipment, but what you see is that there's two other pieces, the green and the purple, the 18% and 20%. The 20% is energy usage. So what that says is that if you're running these servers for 24 hours, 365 days, and your energy costs are 10 cents per kilowatt hour, and in many places it's much higher than that, then about 20% of your 3-year cost of ownership goes towards paying your energy bill. The other piece that most people miss is that 18% green number. People don't build data centers because they look cool. They build data centers because that's where they house their servers. So there's a capital expenditure, roughly somewhere in ballpark 10 million per megawatt, that goes into the construction of these data centers. And this is mostly power distribution and cooling. So this doesn't include any of the server costs or the network equipment costs. So then if I put a server in there that is a 500-watt server, I need to look at the depreciation on that capital expenditure and allocate that in proportion to the power that's provisioned for that server. So that green chart, the 18%, is that capital cost attributable to the server that's in the data center. So you can see about one-third, more than a third of the overall cost of ownership is energy related. And that's based on a 3-year life cycle. Many people do not update their servers on a 3-year life cycle. If I were to do this for 5 years, that green and that purple bar would be even higher and get close to about 50%. So energy does matter. And because of all of that, in 2014, US data centers consumed about 70 billion kilowatt hours of electricity. And that has stayed relatively flat for the last 3 years or so. And the reason for that is the energy efficiency has gotten better. But lately what you see with the introduction of these 180 and 200 watt processors, we've lost sight of the energy equation efficiency. We've lost sight of the fact that we need to limit the amount of energy being consumed in our data centers. And I think that's somewhat irresponsible. So we need to focus more on energy efficiency to make sure that we stay within some reasonable bound. So once again, energy efficiency is important. Average power matters, not just the peak power. So a little bit of a commercial message here, so excuse me, I'll run through this very, very quickly. Qualcomm had to pay my flight bill, so I had to put 2 slides sort of talking about our product, so bear with me. So our first product, we're very proud of the fact that it's the world's first 10 nanometer server processor. That's a technology statement, right? It's 48 ARM V8 cores running at 2.6 gigahertz. These are custom designed cores. These are not licensed cores from ARM. They're specifically designed for servers. They're 64-bit only. We jettisoned the 32-bit part of the design to allow us more power and more area that could be dedicated for a 64-bit server performance. I won't go into a lot of the details. There's a link at the bottom. You can go check it out yourself. Like I said, I didn't mean this to be a sales pitch. But if you look at the results of what we were able to achieve versus Intel Skylake, I think this is my last slide that shows how we do competitively. But it's important to know, if you set your heart to being energy efficient, what can you deliver? It doesn't mean that you're going to sacrifice performance. If you look at all of the Skylake SKUs that Intel has, there's about 30 or 40 of them. There's only 3 of them that deliver higher performance than our Centriq 2400. And our Centriq 2400 is a 120 watt part. The 3 Skylake SKUs that have higher performance are 165 or 205 watts. But in order to make things a little interesting, what I did was, let's compare to the top end Skylake SKU, which is the Platinum 8180 with 28 cores, 205 watts, 775 spec int rate. Yes, what does that translate to? 18%, the yellow bar is spec int rate, 18% higher performance than us, but they're at 205 watts, we're at 120 watts. But then if you go to anything like performance per watt, performance per thread, performance per dollar, and the performance per dollar is based on list price. And yes, there are many people who don't pay the list price, but that's the best I could do. So you can modulate that number any way you want. Now, performance per core, yes, they're 2x, but nobody's going to, since not all the cores, not all 28 cores on Skylake are going to be running at that full frequency. That's kind of a hokey number. So spec int rate per core is a much better metric. So then you take the next one. I said, how do we compare if we do it at the same power level? We're at 120. I picked their highest performance 125 watt part. And now you see that all of those metrics, except for performance per core, are very much in our favor. Yes, their overall spec int rate is 4% higher, which is close enough. Then I said, let's take their top E5. They used to have this E5, E7. E5 was their family of 2-socket processors. E7 was the 4-socket. And if you took, and the E5, the top price point was about $4,000, $4,700 or something like that. So if you took the SKU, and with Skylake, they went to this silver, gold, platinum, and it kind of can get very confusing. So I picked the the top SKU that sort of was at the price point of the old E5, which is now the 8160, and that's at 150 watts, $4,700. And again, you can see that except for the performance per core, our chip comes out looking ahead. So on performance per thread, performance per watt, we beat all of these. And then the last one, I said, let's do it ISO performance. Ours is at 657. These are, by the way, GCC O2 measured numbers. Theirs is at 653. So ISO performance, ISO power, and at 2 different price points. If you pay attention to energy efficiency, yes, you can deliver competitive performance without sacrificing at a lower power, without it being a lower performance. When ARM servers first came about, people started talking about microservers. That's not where the action is. That's not where the large cloud service providers are focusing their deployments. So the important thing is being able to deliver top-level performance compared to the Intel products at a much lower power. And that's what we're doing. The other thing that matters, remember I told you about the energy consumption. Now, we measured the power running the spec-in workload, which has about 12 different subtests. And across each of the subtests, what we noticed was that the average power consumed when running the entire test is slightly more than half the thermal design point. So why is the thermal design point at 120 watts when the average power is about 65 watts? That's because a lot of these workloads are peaky. So for a very short period of time, they get close to that above 100, 110, 115. So from a thermal design, you have to be able to tolerate a maximum power dissipation of 120 watts. But on average, in our case, it's significantly lower than that maximum power. So TDP is max power. The average power is significantly less. And then the other thing we do is the idle power is 8 watts, which helps a lot in the energy. So before we move on to the next phase, I thought instead of giving you my opinion and a lot of answers, I'll put some questions up there. I have my opinion, but I'm not going to share that with me. You can catch me after the presentation. I'll tell you what I think. But top of the list is, are we really serious about energy efficiency? If we are, why are people buying 200-watt processors that do not deliver good performance per watt? The lowest performance per watt on those other SKUs that I showed you are at the ones that are at 205 watts. What should the cost and power constraints be for people who are designing these processors? How many instruction sets is too many? We have x86, we have ARM. I think MIPS, at least in servers, is non-existent. Power's trying to make a comeback. There was an Open Power Summit last week, and they're talking about deployments at Google and other places. And then the other one that's sort of coming on, at least somewhat strong, not in service quite yet, is RISC-V. The other question is, have we reached the limit of high core count? With each generation, if the only way we can get throughput performance is by increasing the core count, where does it stop? Can the software handle 150 cores? I mean, does it need to be capped at some 2-digit number? How does the software scale when you get to 100 cores on a single piece of silicon, constrained by the memory bandwidth? Memory bandwidth isn't growing at that faster rate. That's something that I don't think we pay enough attention to. Do we need to improve the single-thread performance for general-purpose computing? Or do we need to focus on new workloads like machine learning and have accelerators provide that level of performance? What should be the power limit be for a single socket? It wouldn't surprise me if the next generation from some companies will go from 200 to 250 watts. Is that the right trade-off to make? And lately, when we talk about security, I don't believe that you can have security without incurring a performance penalty. The question for us as an industry is, how much performance are we willing to sacrifice to get security? And one of the reasons some of these security things happened was because from an economics perspective, we said multi-tenancy is the way to go. So when you combine multi-tenancy and some other, speculation, we found ourselves with the problems that we have today. Yes, these problems can be solved, but it will cost, maybe it will cost in cost area, it will certainly cost performance. How much are we willing to sacrifice in terms of product cost and performance to get security? We better be willing to answer those questions. Cost and convenience, I covered that. The other thing that I think about being a semiconductor guy is when does device scaling end? 7 nanometer is showing up now. We haven't seen the first server processor in 7 nanometers, but you'll see that before the end of this year. 5 nanometers beyond that, and the next will be 3. Will 3 nanometers happen? I don't know. Will there be a sub-pico nanometer? Will we have transistors below 1 nanometer? I don't know the answer to these questions. So these are things to think about. So now let's move on to the heterogeneous computing era. There are a lot of lessons we can learn from the world of mobile computing. First of all is energy efficiency has to be an implicit target. When my colleagues at Qualcomm design chips for the smartphone, they have a power budget, 1.5 watt, 2 watt, or whatever it is. And their job is to deliver maximum performance within that. In my world, in servers, yes, it's a 3-digit number, but our marching orders are, here's your power budget, here's your area budget, how much performance can you deliver within that? If you start with desktop CPUs and scale those to do either mobile, there's a reason why x86 doesn't play in smartphones. If you look at the server products, they're not energy efficient because they're essentially power-hungry desktop cores. On the other side, you can't use Wimpy mobile cores and win in servers. So we had to sort of move away from our mobile cores and design a server-specific core to meet the needs of servers. But you can design those server processors using the same mentality that you use to design mobile cores, where energy efficiency is a very explicit design goal. The other thing what we notice in the world of mobile computing is that many workloads run better on different. So we have a DSP, there's a GPU and a CPU in the mobile SoCs. And depending on the workload, you run those on these different engines. Why can't we do that in the server domain also? And that might be a better way of pushing performance than just adding more cores. So we're now in the age of application-specific accelerators. You've started to see TPUs. Google sort of has made a big deal about their TPU and how deploying those TPU has allowed them to reduce the number of servers that they're deploying. And in general, you can get an order of magnitude higher computing efficiency with a specialized engine than you would with a general purpose engine. This has been true in the industry for a long time, but back in the old days when the single thread performance was moving at a very rapid pace, what people who were doing highly specialized processors found out that the next year's general purpose processor would catch up to what they were trying to do. The volume wasn't there, but I think things are changing. So what's important is that because you have an order of magnitude improvement, you don't necessarily have to go with the most efficient implementation of these application-specific accelerators. Time to market is important. So I would leave 10% performance on the table to get to market 6 months sooner. There are many potential applications. Machine learning, encryption, data compression, video processing. These are not meant to be a complete list. And in order for this to be viable, you need reasonable volume. If you can't sell enough chips, you can't amortize the development costs of doing an accelerator. What you see is many startups now raising on the order of $50 million for their first machine learning accelerator product. So the rough cost of developing a specialized chip for artificial intelligence is somewhere in that $50 to $100 million. The other thing is the algorithms have to be stable. Because if the algorithms are changing, if I was going to build something that's application specific, and I pick an algorithm today, and I'm not going to ship it for 2 years, if in that meantime the algorithm changes, nobody's going to want to buy my part. So there are challenges, and sometimes if they're fixed function, that makes it difficult too, and that's why for some people, the FPGAs are a better fit. So how did this all get started? I mean, we've talked about machine learning for a long time. And I was a graduate student at Carnegie Mellon in the 70s. It was all about playing chess and Go and speech recognition and all of that. But there was nothing that was large and commercial. But there are three things that sort of happened within the last 5 or 6 years. There was more data available to analyze and figure out how those workloads behaved. We had better models to deal with. And then it just so happened that the GPUs were there. They weren't designed specifically for machine learning, but it was better than trying to develop your own. And there's a lot of excess baggage in those GPUs, which is not relevant for machine learning. I'll talk about that a little later. And that allowed people to do some very interesting things. And the turning point, in my belief, was a presentation at the ImageNet competition in 2012. That opened people's eyes, and now, everybody's doing deep neural networks. Now, here's another chart that shows how, over time, the interest in machine learning has evolved. On the left-hand side, this chart came from Google. The number of people doing search with the term deep learning, you can see how that accelerated from 2010 to sometime 2015. The use of deep learning inside of Google also took a big turn, and that's why Google launched their TPU and the TPU2 internally designed. They had a captive market. So devices, machines, and things are all becoming more intelligent. So then the question is, where do we put the intelligence, and what are the parameters? I'll skip this one in the interest of time. So where do we need to put the compute, and why? And then this is all general purpose as well as special purpose compute. Clearly, there's computation available in the device itself. Today's smartphones are doing inference on the phone. In the past, when you tried to do something on your phone, what your request got sent up to a server in the cloud, the results came back to the device. But now a lot of that is happening on the device itself. We all know about the central cloud, but an emerging trend that I think often we miss is this thing in the middle, the computation at the edge. And I think you heard Mark Shuttleworth talk about how the edge is going to eat up the cloud. I'm not sure it's going to be that drastic anytime soon, but essentially you'll see a lot of computation happening at the edge, primarily because of the latency and the availability of compute resources closer to where the devices are. So what is the edge, right? The edge is essentially a bunch of servers that are closer, like I said, to the devices. The latency is maybe 5 or 10 times lower than sending that request to a central cloud. They're smaller, fewer racks. The power budgets are smaller. They want server processors that are maybe less than 100 watts. They can't tolerate the 200 watts because they're severely space and power constrained. So this is sort of an interesting dynamic that you'll see playing out, where the telcos will start kind of figuring out how to provide that same level of functionality at the edge that a lot of the cloud service providers are providing at the centralized level. So AI is everywhere. And inference is happening on the device, at the edge, and at the centralized cloud, again, depending on the use case. There isn't a single answer that everything will be done in one place or the other. So what are some of the silicon alternatives for deep neural networks? Clearly, the most flexible is the CPU. And a lot of people are doing that on the CPU to the extent that there are unused cycles. If you look at most data centers, the CPU utilization is fairly low. So if you've got free cycles, and if you can get the inference done in a reasonable amount of time, not necessarily the fastest, that's one place to do it. There are ISA enhancements. ARM has talked about some of those. Intel has mentioned what they're doing. And you can complement the servers with some accelerators like the TPU, et cetera, to make it even better. GPUs have been used mainly for training. For inference, they're too power hungry and too expensive. The part in the middle, which is FPGA, has the flexibility. They don't cost a lot to develop, but the unit cost is slightly higher. And they're not easy to program. On the other extreme, the most efficient one is an ASIC, but it takes you maybe a year and a half to develop it. Yes, it is more energy and cost efficient, but it costs you a lot of money, $50 million to $100 million to develop that chip. And it's the least flexible. It's a damn good job for it was designed for, but it can't do anything else. So how do you see this, and how do I see this playing out? GPUs and large DPUs, DNN processing units, higher cost will get deployed for training. But on inference, and the volume is lower. So it's lower volume, higher price versus higher volume, lower price at the other extreme for inference. So inference will move more and more towards smaller, lower cost, lower power, specialized engines. I think training GPUs are still at the top, and there are at least a couple of startups that I know of that are doing something specific, essentially removing some of the things in the GPU that do nothing for machine learning to essentially get more done with less silicon area. So what are my sort of final thoughts on silicon design for deep learning? CPUs are not powerful enough, but they have free cycles. But there's an opportunity for add-in accelerators. Instruction set enhancements, as I mentioned before, will improve the performance of initially of inference on the CPUs. Initially, it will be through add-in cards. Sometime in the future, you'll see multiple chips within a package, so package-level integration. And then some years beyond that, you might even see these specialized accelerators integrated on the same piece of silicon. GPUs, in my opinion, have too much extra baggage, and that creates an opportunity for domain-specific accelerators. FPGAs will find a place because they're much more flexible, and they have a faster time to market as long as you know how to program them. So deep neural networks are really moving into many areas, drug discovery, medical imaging, beyond sort of saying, this is a picture of a cat, which is how most of this stuff started. But we have an opportunity to dramatically reshape the way we design our computing devices to meet the needs of this emerging and growing market. I expect to see lots of innovation and excitement in the years to come. So stay tuned. It's going to be a fun ride. So in conclusion, single-thread general performance improvement is slowing down. Energy efficiency is extremely important in data centers. ARM architecture enables energy-efficient designs with good performance, but that has to be a very explicit design goal. Typical use efficiency is becoming more important than peak performance at the highest levels of power. Idle mode power will become more important. Smart power management is also something that will help limit the energy consumption in data centers. Security improvements are needed, but we'll have to accept some performance loss to get that security. Nothing in life is Nothing good in life is free. There's plenty of opportunity for innovation, for new application-specific architectures. And then as I was thinking about this, I said, not just in CPU design, but in life, speculation can lead to a meltdown. So that's all I had. So I don't know whether you have time for questions or people can catch me after. I'll still be around. My flight is until this afternoon.
That would be terrific. Thank you so much. OK, so for our next speaker, we have Laura Dekker with us. Laura is going to talk to us about another very interesting and very different subject, the machine as an alien ethnographer. I never considered that before, but I think it's really interesting. Certainly, she spent some time with it, and she's going to share her insight with us. So please join me in welcoming Laura Dekker. Oh, the button? You left the button.
I just need to fiddle a bit first. Okay. All right. Okay. So, wow, there's so many people here still. I'm really impressed. Yeah, thank you for being here, and thank you for inviting me. And Cantor, I know you can't hear me because you're on a plane, but thank you for bringing me here. Yes, so I'm going to talk about the machine as alien ethnographer. I was thinking about the work that I do. I have a technical background, but I'm a working artist now and using technology in my work. And it seemed that machine as alien ethnographer seemed to kind of speak about what I tend to do. So originally, I was working in the Intelligent Systems group at University College London, which is when I met Cantor. We were both working on genetic algorithms at the time. And then I got more involved in the machine vision side of things, and then I spent quite a few years working on 3D imaging of the human body, and then worked in commercial R&D, and then set up a company to do that. And then after some time, when we sold that company, I suddenly thought, actually, there's this whole other side that I want to explore. And I decided to study fine art, which I did at Central St. Martin's in London, and then more recently at Goldsmiths College in London. And since then, I've been working as an artist all around the world, mostly festivals and some work in kind of white cube galleries, but mostly out and about in quite unusual locations. So that's enough of me. What I wanted to start with is, you might recognize this. It's an excerpt from an ancient encyclopedia called the Celestial Emporium of Benevolent Knowledge, in which it's declared that animals can be categorized into exactly 14 categories. So those that belong to the emperor, those that are embalmed, tame, suckling pigs, mermaids or sirens, fabulous, stray dogs, and this one I really like, included in the present classification, frenzied, innumerable, drawn with a very fine camel hair brush, etc. Having just broken the water jug, and finally, ones that from a long way off look like flies. So. So if you recognize that, it may be because it's from an essay by the Argentinian writer Borges. And if you haven't read anything by him, then you must, because he's absolutely brilliant. Some of them are just half a page long. And in that half a page, he can set your mind off on amazing journeys. another place you might have seen it is in Michel Foucault, the philosopher, in his book, The Order of Things. He talks about this, not because it's amazing and absurd, but he says that this short passage shatters our usual way of thinking, and in this amazing exotic taxonomy that Borges presents, it's not just the charm of that alien taxonomy, it's actually that it suddenly makes us realize about the limitations of our own thought. And so that's kind of the background behind what drives most of my work. This idea of thinking, kind of trying to think outside of usual ways of thought. And there's quite a big philosophical movement in the last 10 years or so, which has got various titles of anti-anthropocentrism, or the posthuman, or the non-human. And it's generally, these schools of thought are about taking the human from the center of thinking and reconsidering what it is to be human. Some of it is technologically driven. So the idea of trying to remove this idea of rigid boundary between human and machine, or generally the tools that we use, and we're not just human, and then the machine is this other thing. We have an extended self that makes use of those things, even some technology as simple as a pencil, or the more sophisticated technologies, which actually, I meant to set my timer, you know, this technology that is an extension of ourselves too. So this is the idea of breaking down barriers, not just in human-machine, but also all sorts of categories that get projected onto us, like gender and sexuality and ethnicity and all those things. So trying to think outside of those boundaries and what it might be to move those. Also thinking about the agency of objects, so not just human as the only thing having agency, but machines having their own agency, and even objects like this having its own agency. So this is obviously, in anything, you're always applying some kind of assumptions and biases, but it's kind of shifting those assumptions and biases in different ways and seeing what emerges. So finally, some of my work. This is just a little example of it. This is a commission that I had in 2013. There's an organization called Secret Cinema in Britain, and they choose a kind of usually quite a cult film, and then they stage this incredibly deep, intensive, immersive experience that you sign up to this. You don't know what the thing is going to be or where it's going to be, and then at the very last minute you're told of the secret location that it's going to be. So they invited me to do this thing for the film Brazil, and I hadn't ever seen the film Brazil, and they said, great, we don't want you to just be too much following the film, but these are the themes that we want you to think about. So I made this thing with these giant eyeballs. So this was projected enormously with this giant tank of giant eyeballs that kind of bobbed around, and then they follow the people around, and they bounce off each other, and kind of you can see their pupils dilating and so on. So the idea of that was really thinking about, so these alien objects are kind of looking out at you and as if they're sort of wanting to interact somehow. This was also at the Era 415 Awards in San Francisco, and there it was projected like about 12 meters wide on the side of a building, which was great fun for me. So back to this idea of the machine as alien ethnographer. So my work tends to be, it's about a non-human entity exploring the human world, attempting to provoke you as an audience member, to play, and also it's about the machine creating on its own terms. So if that's possible, the idea that a machine might be creating things that are not controlled by a human, and if a machine might have its own aesthetic. So we not quite even sure if that's possible, but it's interesting to think about it. So in doing that, I think I've found computation as an artistic tool has its very particular thing that you don't have with other art media, is that in computation you can do pretty much any kind of transformation that you want to do. And then because the machine is basically just manipulating a symbol which you can interpret in any way, that automatically makes it possible for things like synesthesia. So you're taking data from one domain and transforming it into a completely different one. So it's just incredibly exciting. It's such a rich area, there seem to be no limits on it. So the tools that I'm using in this, so mostly open source stuff. I work a lot with open frameworks, C++, and increasingly with Python, because Python's brilliant for natural language processing, and I use a lot of open data sources, and lots of, so I was going to do a demo, but I'm not actually going to do that today, but normally I'll be using a lot of sensors and actuators as well in the work. And also, because I don't want it to be just about machines, there's also, or kind of blurring the boundary between a machine and the rest of the world, I also bring in quite a lot of organic stuff, so even rotting organic matter and so on. I'm not interested in slick. I'm going to quickly hop through these ones because I don't think there's too much time. I'm going to hop through to some more recent stuff. Yeah, so one of the other things I'm interested in is in the kind of the discourses around AI and in like popular conceptions of it, and also how the media treat it. And this was a piece of work I did 2 years ago, because I'd been looking at media output about AI, and I realized there were so many stories that were hyping it and trying to instill all sorts of fear into everybody. And there seemed to be kind of 5 different categories of the way that the media would report about AI. So eventually, I was collecting these headlines together, and I decided to make a piece of work about it. And the categories seemed to be, number 1, will a robot take my job? Number 2, would you have sex with a robot? Number 3, it was about AI ethics. And number 4 it seemed to be about kind of how AI would relate to the rest of the living world. So I saw that there was, at the time, the Dutch police had been training bald eagles to take down illegal drones. And the final category, there was an article in IEEE Spectrum about what Alan Turing really thought about AI. So I collected these together and decided to build 5 little robots that would each be an actor and act out one of these headlines. So this was a show that I was involved in called Technology is Not Neutral, with these. So these are the 5 little robots that are moving around. So I designed and programmed each of them with various different capabilities to kind of try to embody those headlines. So there's this one here is the Google AI. Sorry, I need to go back to remind myself what the headlines were. Yeah, so this was an article in the UK's Daily Mail called Google AI Ethics Board Remains a Mystery. And so the kind of the little policeman there is representing the Google AI Ethics Board. On the right, would you have sex with a robot? It was this little thing that it had a sort of a capacitive touch sensor shell, so that if you stroked it, it would emit kind of cooing sounds. The second from the right actually, it's hard to see in this light, but it's kind of piled up with hundreds of tiny little figures of people. That's the "Will a robot take my job?" And in fact, on the BBC Online, you could actually type in stuff about your job, and it would give you a percentage likelihood that your job would be taken over by a robot. And mine was luckily quite low, which was only 4%. And then, so there's, in the middle, there's the trained bald eagle taking down a drone. And then on the left here is Alan Turing. So they would interact with each other, sort of follow each other, and have confrontations. And in the end, actually, they were running for 3 months, and they ended up being I kept having to go and repair them because they got quite battered. And children quite like to grab and pick them up as well, which was fine. It's one of the hazards of doing public artwork. So this is what I'm going to go into in quite a bit more detail. This is a work that ongoing work that I've been doing for the last year and a bit. And the idea is that there's this machine that has built itself from all sorts of discarded parts, and it's then trying to explore the world in which it's found itself. So it's, with its camera, it's looking around, and it's tasting what it sees in the world. And then in response to that, it writes poetry. So there's it's projecting its poetry down onto the floor, and those taste meters are showing the different taste levels of what it's seeing. So I trained a neural network to associate. I trained it with video clips of. It's all based around this idea of something generating itself from rubbish or discarded things. So I trained the neural network on rubbish heaps, compost heaps, rotting and discarded things. So I assigned different taste values to the different types of rotting stuff. And then based on those values, so there's salty, bitter, sweet, sour, and umami. It takes those values and uses those as input to choose what words it's going to use when it's writing the poetry. So in this version, I used a genetic algorithm for the poetry, but I've been working on using Markov models now, which actually works. It makes slightly more human intelligible poetry than the genetic algorithm was doing. So it projects the poetry onto the floor, and it also has a little thermal printer for printing it out too. And now I'm going to see, right, it should be running here. Yeah. So that's what it's seeing at the moment. And, oh. Yeah, so you can see this is the output values from the neural network up there. And at the moment, you're quite sweet and quite umami, so that the number 2, so top one is salty, then sweet, then bitter, then sour, and then umami. And that's interesting. Yeah, the left and the right side are slightly different. And then on the right here, I have to say, I'm sometimes when I see what it's writing, I'm quite embarrassed. But it seems to be safely not too, there are some words in here so I've fed various different books into it, and some of the vocabulary is a little bit risque, but at the moment it's not. That tends to be the salty word. So actually, at the moment, salty is quite low, and so it's not too sexually explicit. So I'll go in a little bit more detail about how I built that. Oh, that's another version of it. Well, actually, we built it in a big warehouse, and we invited people to bring in old bits of technology, and we built this enormous heap. So the heap was about that high and about 4 meters long, all sorts of ancient computers and junk. There was some Commodores, and at the end, we invited people to come. They could take stuff off the heap and take it home if they wanted to. Everybody wanted these old Commodores, but actually they weren't available because the person who donated them wanted them back. But lots of people were coming in and looking at all the stuff in this heap and saying, wow, I used to have one of those phones. And they were really enjoying just looking at the junk in the heap. So this is the kind of general structure of this machine, and it's based quite a lot on Daniel Dennett's view of the human consciousness. So this idea that there's no centralized control over the thinking, and there are these greedy processes that are seeking input and producing their output without an overall controlling structure. So in this example, so I have various ways that the machine can take input, and it processes it and stores those in internal states. And then there are these processes that will express the machine's inner states based on the data that it's consuming, and then feeding that to various output devices. So in the various perception modes, these are some examples. So I'm taking input from the webcam there, compressing it, and then feeding it to the neural network, and which produces the taste values, which are stored, and then those are picked up and used when it's expressing itself. And this is the structure, how the Markov model that you were seeing the output from is working. So I trained it on various text sources, which then feed into the production process. So it's based on the probability in whatever the text inputs were. When it's producing a new piece of output, the words that it chooses in the next step depends on the probability of what was fed in the source texts. I also make use of an extended vocabulary, so depending on what what the current stimuli are, it will choose vocabulary from different categories of data. So the sweet words are chosen from one vocabulary set, salty, bitter, sour, and umami, and so on from different vocabulary sets. So the umami words are taken mostly from technical sources. So, for example, programming in C++ by Paul Cholian, some of the words from that, those have gone into the umami vocabulary set. And I particularly like words like that have meaning in normal usage, but also have very specific technical usage, like void and member and private and overload and so on, which produces the kind of ambiguity of those, produces quite interesting text. And I'm running out of time, so just finish off. Where I produce these artworks is incredibly varied. Sometimes I work in woodland and parkland, and that's just a nightmare in terms of trying to get this equipment into these places with no power sources. So I've had Connects and Macs up in trees and using enormous portable battery sources to try and get these things working. And there are particular challenges in various, like working in a heritage property where you're not allowed to drill into walls or anything like that. Each time is completely different. And so, yeah, I'm going to close here. So generally, I'm working using art as a kind of a tool for critically analyzing things and trying to see things from a different viewpoint. And being here this week, I realize as a consumer of open source stuff, I feel the need to put something back into that ecosystem. Not quite sure, I mean, apart from doing bug reports and stuff like that. And yeah, the last thing I wanted to say was it's actually a quote from an Italian philosopher who, she said that this idea of the thinking of the post-human, it's an opportunity to empower the pursuit, so this is a direct quote from her, to empower the pursuit of alternative schemes of thought, knowledge, and self-representation, to think critically and creatively, so to develop a more sustainable relationship with the planet and its other inhabitants. I'll finish there. So thank you for listening.
Thank you so much for coming and sharing with us this morning. Do you have the last slide that you can put up? All right, no big deal. Okay, so for those of you who, there are some people I know that are headed to the airport, and if you're not going to join us for Demo Friday at noon, thank you for coming this week. We really hope you had a great week, but hopefully you'll be able to stick around and see the final of the festivities, have some good food and drink, see some fantastic demos that a lot of people have worked on. So we'll be in this room over here at noon. And starting at 10 o'clock, there'll be the TSC meeting, but no, I'm sorry, it'll be in this room at noon, on this side, ballroom number 3. And starting at 10 o'clock,